Hello all. Let us do two problems dealing with rate law. One will be pretty easy, the other one will be more challenging. The first problem is shown here. From the data table, determine the rate law, part B, overall order of reaction, and part C, the rate constant K for the reaction. Now, what we need to do is we need to find two trials. Here we have trial 1, 2, 3, 4. And actually, let's set up the rate law expression. We have rate equals K, concentration of NO2, to the M, concentration of CO, to the N. And to complete the rate law equation, we have to figure out M, and we have to figure out N. Later on, they're going to ask for the K. So I would imagine that for part A, we just need to figure out M and N, and then for part C, we'll figure out K. So just for part A, when they ask for the rate law, M and N. Let's tackle NO2 first. The idea is to find two trials where NO2 changes, but not CO, and then the change in the initial rate will be based off of the change in NO2, since we're picking two trials where the CO is constant. And quite easily we can see maybe trial 1 to 2, because here from trial 1 to 2 the concentration of carbon monoxide is identical, and then here I'm going to do this the quick and dirty way. We multiplied it by 2. What do you notice about the initial rate here? It actually goes up by, the way you want to do the math is you take the bigger number, 0.0082 divided by 0.0021, and it went up by around 4. Okay. Again, we're doing this the quick and dirty way. We'll see if it's close to an integer, then we'll keep the order as an integer, like 0, 1, or 2, or it may be a decimal. We don't know for sure just yet. So what happens here is that we went up by 4. What that means is that the initial rate did not track directly with the change in the concentration. It actually went quadruple when we doubled the concentration. What that means is that M is second order. M equals 2. Okay. Actually, I might try to do this mathematically just to prove that this is actually very, very close to 2, and we can just round to 2. But let me do this again the quick way. For the concentration of carbon monoxide, you want to pick two trials where the NO2 stays constant, and that would be maybe these two. And I'll go to the other side like this. And here we have the concentration of CO double. So again, we put times 2. And then, ooh, look what happened here. From trial 2 to 3, there was no change. So this went, well, there was no change, so that's really times 1. What that means is that if the rate is independent of the change in concentration of a reactant, then in that reactant, the order is 0 with respect to that reactant. So therefore, N equals 0. The final answer for part A would be rate equals KNO2 squared, and then since anything to the 0 is 1, you just leave it blank. That would be your final answer if they ask you for the rate law, knowing also that we're going to calculate K anyway for part C, so we don't need to calculate K right now. The overall order of the reaction, this is, I'll put part B here, give us some space, it's just the exponents added up. So M plus N equals the overall order. and m is 2, n is 0. So you could say that it is second order overall. So true, it's second order in respect to nitrogen dioxide, but it's also second order overall because n equals 0. We get this from 2 plus 0. How about the k? The k is a constant that applies to every trial, and it is constant. It should work for any of these trials. So just randomly, let's pick trial 3. Trial 3, you're just plugging in and calculating for k. For trial 3, the rate is 0.0083, and just keep track, it's molarity per second, equals k times the concentration, but we have a number for concentration. It is 0.2. Don't use brackets. Brackets means concentration. So we just take 0.2, the numerical value, and we square it. K equals, I'll write it off to the side, 0.0083. Let's see, divided by 0.2 squared. Double check my math. K equals 0.2075, or we could round to let's round to 2 digits, 0.21. And then the units. See, this 0.20 is molarity squared. We could write that down somewhere. This is m squared. We really want the initial rate to be m over s. So what does k have to be? K has to be 1 over m times s, or you could do m to the negative 1 times s to the negative 1. That molarity in the denominator will cancel out one of the molarities in the numerator, leaving us one molarity up top. Okay. Oh, I think I said A, B, and C. Mathematically, okay? Mathematically, let's go back and figure out this m for real. Like, is it really that close to 2? Well, we used trial 1 and we used trial 2, right? Is that what we used? Yep, it's the green one here. So I'm going to pick the bigger number. Remember, its rate of one experiment over the rate of a second experiment equals the concentration of the reactant in the first experiment divided by the concentration of the reactant in the second experiment times, not times, but raised to the m. And then you're going to solve for m. So again, I typically want the bigger number on top, the bigger rate. So I am going to go rate 2 over rate 1. Why don't we just plug in numbers? So this is, can I get everything on the screen? This is 0.0082 divided by 0.0021 equals, now just remember we're using trial 2 on top, 0.20 over 0.10 to the m, and then we could go ahead and simplify. 0.0082 divided by 0.0021. Okay, so this is 3.905 equals. Obviously, this is what? This is 2 to the m. So yeah, it's close to 2. 2 to the 2 is 4. But how do we do this mathematically? It's the log of 3.905 equals m to the log of 2. So we'll calculate the logs, or we could do this directly. Log 3.905 equals, divided by, I'm a little worried, maybe I should, let me try without parentheses. Log of 2 equals m. M equals 1.965, and that is close enough to 2 that you can, oops, I'm off screen, close enough to 2, you can say that it is second order. Now if it was 1.7, you can't round out to 2. Or if it was 1.3, you can't round down to 1. So this was the easier of the two. I'm giving you a hint that this one we may need to do the math that we just did, where we did rate 1 over rate 2. Maybe. We'll see. Same instructions. Let's write the rate law. Do you want to do this before I do this to test yourself? If you want to give this a shot and you understood how I did the math right here to get the exponent, go ahead and pause the video and come back and compare it to how I would do it. Okay. Let me get down the rate. I feel a lot more comfortable if I have the rate law in front of me. CHCl3 raised to the m times Cl2 raised to the n. And yes, we got to figure out m and n. Let's start with CHCl3, that is chloroform. And okay, again, trial 1 and 2 are good because here we double, but here we don't change, and here we double, right? 0.0035 times 2 is 0.0070, which is close to this number here, times 2. They match. The rate tracks with the change in concentration. You would expect that m equals 1. Okay. Right now, I'm not going to do the math for the CHCl3. I think it is m equals 1. Let's take a look at Cl2. And again, we're doing this again, right? The trial 2 and 3. That stays the same, but this is the one that doubles. And now this one, I'm going to need my calculator. 0.0098 divided by 0.0069, it went up by 1.42. Times 1.42. So it's not tracking quite with the concentration. It didn't go up by double, but it didn't quadruple. So it's not first order, and it's not second order. If it was second order, this would go up by 4. It's not zero order because this would go up by 1. It wouldn't go up at all. So we would say that we would expect n to be in between 0, right? If it was zero order, this would go by 1, or first order, 0th and first, because if it was first order, this would have doubled. Okay, very interesting. Let's go with the math then. We are using trial 2 and 3, and the bigger rate is trial 3. So I'm going to go with 0.0098 divided by 0.0069 equals concentration 0.020 divided by 0.010 raised to the n. N is the one that is not an integer for sure. Am I doing this right? That's since this doubled while this doubled, that's first order. This did not double, it's below doubling, so it's less than first order. Okay. Alright, just have to do the math. Oh, I already did that math. 0.0098 divided by 0.0069, that is 1.420 equals, this is 2 to the n, and then take the log of each side, log 1.420, what is this? Equals n to the log of 2 again. Why did it end up being 2 again? It's because the concentrations, when they divide them, one is twice as big as the other. But anyway, log of that 1.4 number divided by log of 2. I'm really well, we're not going to get an integer, I don't think. 0.51. So n is a half about. N equals 0. We'll go 51. All right. So what is the rate law? We finally have to put everything together. Rate equals K, concentration of CHCl3. It was to the 1, M to the 1, and times, interesting, Cl2 to the 0.5. We'll round to one significant digit. That's why this was a little more challenging, because we're raising to a non-integer, 0.5. Okay. Overall order, very interesting. For B, remember it's all the exponents added together. So this is 1 plus 0.5 equals 1.5. That is the order of the reaction, overall order. Part C, figure out the K. And yes, you do need to put units. Any experiment, 1, 2, 3, 4 doesn't matter. We used 3 last time, let's use 4 this time. Okay, those are your numbers for 4. So you're just going to plug it in. The rate equals 0.00. Nope. The rate equals 0.027. I'm getting it from right there. Also double check your units, molarity per second. Equals K times. Oh, this is nice. We're going to take it to the raised to the 0.5. So we have concentration of CHCl3 is 0.040. That wasn't raised, well, it was raised to 1. And then Cl2 was 0.040 raised to the 0.5. K equals. Let me show you this first. So I'm going to do that one right there. 0.040 caret, like a little hat, 0.5. I hope this works. Okay. Times this one, 0.040 equals that. And that goes on the bottom denominator. So 0.027 divided by the answer we just got. K equals 3.375. Oh, man. The units. Oh, this is more challenging than I thought. I wasn't prepared. The units will be kind of difficult. Well, if you think about it, you have on the left-hand side molarity per second equals some K times molarity raised to the 0.5. When you do that, are you just adding? Oh, my math is so bad. Alright, so that is the same as m over s equals k m to the 1.5. Let me double check that. 0.040 caret. So I'm just going to use this as an example. They're both the same. Is 0.2 times 0.040. So it's 0.008. Is it true that this to the 1.5 is that number? 0.040 to the 1.5. Okay. I'm surprised I knew my math. How do I figure out K? So it's M over S, and you divide by this, right? So you could say times 1 over M to the 1.5 equals K. What that means is that this m cancels out and we're left with 0.5. The units of k are, um, let's do the seconds here first. I know seconds is on the bottom. And then this cancels out, and then we're left with m to the 0.5. Very sloppy. Or 3.375 s. No, let's do m first. So you take the inverse. Oh, not the inverse, but you do the minus trick. 0.5 dot s minus 1. Circle your answer. Make sure you have the units. Okay, that represents one of the more challenging rate law problems because, again, one of your exponents is not a whole integer. And then you saw how much I struggled figuring out the units for k, but this is the units for k in this case.